This is the first part of the topic, Green's function. In this lecture, we are going to derive the Green's function for a second order boundary value problem. Consider the problem consisting of the differential equation Ly plus phi of x equal to 0 for a less than or equal to x less than or equal to b, where L is the differential operator. L is equal to d by dx of p into d by dx plus q. That is, the derivative of p into d by dx is nothing but p into d square by dx square plus uh, dp by dx, that is p dash into d by dx plus q. Okay. Together with the homogeneous boundary conditions alpha y plus beta y dash is equal to 0 at the endpoints of the interval AB. Okay, for some constants alpha and beta. So we are considering the boundary value problem Ly plus phi of x equal to 0 along with the boundary condition alpha y plus beta y dash equal to 0 at the boundary points x equal to a and x equal to b. Okay, for some constants alpha and beta. So Ly plus phi of x equals 0 means that we have L equal to this. So Ly plus phi of x equals 0 is Ly is p into y double dash d square by dx square of y double y, that is y double dash, plus p dash into this is dp by dx, that is p dash into d by dx of y, that is this will be Ly. Okay, uh, y dash plus q into y. This is Ly. So our differential equation is Ly plus q of x is equal to 0. That is p y dash y double dash plus p dash into y dash plus q into y plus phi of x equal to 0, along with the boundary conditions at the point at the boundaries a and b. Okay. Now here our aim is to find a Green's function g, which is given by for a given number zeta. The Green's function is given by g of x zeta is equal to g1 of x for x less than zeta and g2 of x for x greater than zeta. So our aim is to find this Green's function g such that or satisfying the following properties. So the Green's function g is a function g of x zeta equal to g1x for x less than zeta, g2x for x greater than zeta for a given number zeta, satisfying the following properties. The first property is that the functions g1 and g2 satisfy the equation Lg equals 0. That is, it satisfies Ly equals 0. G1 and G2 satisfies Ly equals 0 in their intervals of definition. So G1 defined for x less than zeta and G2 defined for x greater than zeta. So this means that Lg1 is equal to 0 when x less than zeta and Lg2 equals 0 when x greater than zeta. So the Green's function satisfies this Ly equal to 0. Okay. Second property is that the function g satisfies the homogeneous conditions prescribed at the endpoints x equal to a and x equal to b. That means the homogeneous conditions means the homogeneous boundary conditions at the endpoints x equal to a and x equal to b. So that means g1 satisfies the condition at x equal to a because g1 is here. This is actually x varies from a to zeta, and here is x varies from zeta to b. So this is actually we can say like that. Okay. So then the endpoints here is a, and here the endpoint is b. Okay. So the second property is that the function g satisfies the homogeneous boundary conditions at x equal to a and x equal to b. Okay, that means g1 satisfies the condition at x equal to a. Okay, and g2 satisfies the condition at x equal to b. Clear? Now third property is that the function g is continuous at x equal to zeta. That means this function, Green's function g is continuous at x equal to zeta, means that g1 of zeta is equal to g2 of zeta. Clear? At x equal to zeta, g is continuous. That is, g1 of zeta is equal to g2 of zeta. That is the third property. And the fourth property is the derivative of g has a jump discontinuity of magnitude minus 1 by p of zeta at the point x equals zeta. That is, at the point x equals zeta, the derivative of g has a jump discontinuity of magnitude minus 1 by p of zeta. That is, g2 dash zeta minus g1 dash zeta is equal to minus 1 by p of zeta. Okay, that is the derivative is not continuous at the point x equals zeta, and the g has a Jumper's continuity. When the derivative of g has the Jumper's continuity of minus 1 by p zeta. Okay, so that is the Green's function. So Green's function is this function satisfying these four properties. Okay, so our aim is to find a Green's function g, which is for this boundary value problem. Okay, the given boundary value problem. Okay, so here we are considering that we are assuming that the functions p, p dash and q are continuous functions, and p of x is non-zero in AB. Okay, we are assuming that p of x, p dash x and q of x are continuous in the interval AB, and also we are assuming that p of x is non-zero in the interval AB. Okay, now to show that when such a function g of x zeta exists, the given problem can be transformed to the relation y of x is equal to integral a to b g of x zeta phi of zeta d zeta, such that one defines the solution of the given problem. Okay, now we are going to show that this function, if such a function g of x zeta exists, the given problem, that is the given boundary value problem, can be transformed to this integral equations, such that this is the solution of the given problem. Okay, our boundary value problem is Ly plus phi of x is equal to 0, along with the boundary condition at x equal to a and x equal to b. So we have two boundary conditions. So here we are going to show that when the function g of x zeta, this function Green's function exists, then the given problem, this problem can be transformed into an integral equation this, such that this defines the solution of the given problem. Okay, for that let y equal to u of x, y equal to u of x be a non-trivial solution of Ly equal to 0. Our the differential equation is Ly plus phi x is equal to 0. So first we are considering that y equal to u of x be a non-trivial solution of Ly equal to 0, which satisfies the homogeneous condition x equal to a. That is the first boundary condition. Okay, the lower boundary condition. So we are assuming that let y equal to u of x be the non-trivial solution of Ly equal to 0 that satisfies the lower boundary condition, and let v equal to y equal to v of x be a non-trivial solution of that equation Ly equal to 0, which satisfies the upper boundary condition x equal to b at the point x equal to b. Okay, so now that is u is the solution of Ly equal to 0, which satisfies the lower boundary condition at the point x equal to a, and uh, uh, v equal to v is the, we say, non-trivial solution of that Ly equal to 0 that satisfies the upper boundary condition. That means the condition at the point x equal to b. Okay, now if we write g1 is equal to c1 ux, our aim is to find that g first. Okay, let g1 is equal to, if you write g1 is equal to c1 into this u of x, and g2 equal to c2 into v of x, where c1 and c2 are constants, that is g is equal to c1 into u of x for x less than zeta, c2 into v of x for x greater than zeta. Okay, then the conditions 1 and 2 are satisfied. We know the first condition is actually lg1 is equal to 0 when x less than zeta, lg2 equal to 0 and x is greater than zeta. So this also, this is the first, this was our first condition. So here we know that u satisfies u and v satisfies Ly equal to 0. That means Lu equal to 0 and Lv equal to 0. Therefore Lg1 is equal to 0. Here g1 is c1 into u1. So L into L of c1 u is also 0 because c is a constant here. Okay, and L of c2v is also 0 since this is equal to 0. So these two conditions satisfied. That means the first condition is satisfied. Now the second condition was g1 satisfies the conditions at x equal to a. That is g1 satisfies the condition at x equal to a, and g2 satisfies the boundary condition at x equal to b. So here we are supposed that, or assumed that U satisfies the boundary condition at x equal to a, and V satisfies the boundary condition at x equal to b. So this condition is also satisfied. So this function, if we choose g1 as c1 into u and g2 as c2 into v, then this function g is defined by this is satisfies the first two condition of our Green's function. Okay. Now what we are doing here is we are just finding or determining the Green's function. For the given boundary value problem. So for that we constructed or we assumed two functions. One is u and one is second is b. The first satisfies the first initial boundary condition, and the second one is satisfied the upper boundary condition, and we constructed such a function. Now we have to verify that these two functions, we have to find this c1 and c2 such that the Green's function or this function g satisfies the properties of Green's function, four properties. So here we have verified that first two conditions are satisfied clearly by using for this function. Okay. Now what about the second and third and fourth conditions? We have the third condition is g1 of zeta is equal to g2 of zeta. That means the Green's function is continuous at x equal to zeta. So we have g1 of zeta equal to g2 of zeta. So we have g1 is c1 into ux and g2 is c2 into vx. So we have c1 into u of zeta is equal to c2 into v of zeta. Clear? From this we can obtain an equation like this: c1 into u of zeta minus c2 into v of zeta is equal to 0. Now the fourth condition is that g2 dash zeta minus g1 dash zeta is equal to minus 1 by p of zeta. That means g has a jump discontinuity at the point x equal to zeta of minus 1 by p of zeta, right? So using these are g1 and g2, will get this c2 into, that is g2 dash zeta means c2 into v dash zeta minus c1 into u dash zeta is equal to minus 1 by p of zeta. So from this we can get c1 u dash of zeta minus c2 v dash of zeta is equal to 1 by p of zeta. Here. Now this is a system of equations, system of two equations with unknown c1 and c2. We know that this system has a unique solution only if the coefficient matrix has the determinant non-zero. That is, the coefficient matrix, the determinant of the coefficient matrix is u zeta, v zeta, u dash zeta, v dash zeta. So the determinant is not equal to 0. So we can denote this as w of u zeta comma v zeta. So which is non-zero. If this is non-zero, then the system has a unique solution. That means this determinant is actually u of zeta into v dash zeta minus v of zeta into u dash zeta, which is not equal to 0. This quantity w is called the Wronskian of the solutions u and v of the equation Ly equal to 0. This quantity w is called the Wronskian of the solutions of the u and v of the equation Ly equal to 0. So the Wronskian of u comma v is nothing but u v dash minus v u dash. Okay, or this is the determinant u v u dash v dash. Wronskian of zeta is nothing but u of zeta, v of zeta, u dash zeta, v dash of zeta. Okay, so that means if the Wronskian is non-zero, then it has a unique solution. Now Wronskian equals 0 only if u and v are linearly dependent. We already know that the Wronskian is 0. That is, this determinant is 0 only if the u and v are linearly dependent. Now by Abel's formula we have this Wronskian w is equal to a divided by p of zeta. Okay, where a is a constant. That is a constant divided by p of zeta, or we can say that w into p of zeta is equal to, or w of zeta into p of zeta is equal to a constant. So we can prove this w into p equal to a constant. So for that we are trying to prove wp, the derivative of this wp is a 0. If the derivative of the wp is 0, then we can say that wp is okay. That is what is we are going to do here. So W into P dash is nothing but we have W is equal to this Wronskian U V dash minus V U dash. Okay, that is here from this we get U V dash and minus V U dash is the W. So W P whole dash is equal to U. This is W into P. Now whole dash is this. So by using the product rule we have P into derivative of u v dash minus v u dash plus u v dash minus v u dash into derivative of p, that is p dash. Now this is nothing but, so finding the derivative of this we get u into v double dash plus u dash into v dash minus v into u double dash minus v dash into u dash. So we can cancel these terms plus u v dash minus v u dash into p dash. So this can be written as p dash into u v dash minus v u dash, that is this, plus p into u v double dash minus v u double dash. So now we need to show that this is equal to 0. Okay, we need to show this. So for that we can use this. We know the differential equation is Ly equal to 0, which is nothing but py double dash plus p dash into y dash plus qy equal to 0. That is what is the homogeneous part of our differential. We are suppose that we are assumed that u and v are solutions of Ly equal to 0. Thus we have p u double dash plus p dash into u dash plus q into u equal to 0 and p v double dash plus p dash into v dash plus q into v is also 0. Okay, so numbering this as a and b, this is actually the number of these two equations. Now our aim is to eliminate this q into u part and q into v. So we are just multiplying this a with the v and multiplying this v with the u, then subtracting. So that is a into v and minus the equation b into u. We will get p into this is actually this term will be 0, that is q into u into v minus q into v into u, that is will be 0 subtracting this. So then we will get p dash into u dash v, this terms. Okay, subtracting this from this by multiplying this. So p dash into u dash v minus v dash u. Okay, plus p into u double dash into v minus v double dash into u. So we are just multiplying here with v and here with u and subtracting this. So we'll get this. So this is nothing but taking this is actually we already obtained here that this is p dash into, from this is actually wp whole dash, right? Wp whole dash is p dash into uv dash minus vu dash, that is p dash into u dash v minus v dash u. So here is negative of wp is actually, so p into u double dash uv double dash minus vu double dash, this is u double dash v minus v double dash u equal to 0 here. Okay, so this left hand side is negative of wp dash because wp is this. Okay, so we have wp dash is equal to 0, that means wp is a constant a, we can choose it as a. So that means w equal to a into a divided by p. A constant is actually the Abel's formula. Abel's formula. Okay, so we obtain that W equal to A by P of zeta. Now that means W is actually U V dash minus V U dash. So this is equal to this U V dash minus V of zeta into U dash of zeta is equal to A divided by P of zeta here. Now we are going to solve the this system 2, that is we are trying to find the values of C1 and C2. Okay, so for that we can use Cramer's rule. So here this determinant is u of zeta minus v of zeta, u dash of zeta minus v dash of zeta here, and for here for to find C1 we can replace this first column by the right hand side 0 1 by p of zeta, that is the Cramer's rule. So this is nothing but the determinant of this is 0 into this, that is 0 minus, that is plus v of zeta into 1 by p of zeta, that is we have v of zeta divided by p of zeta divided by determinant of this is nothing but this is Wronskian or negative of the Wronskian, right? That is here we have negative of u of zeta into v dash zeta minus u dash zeta into v of zeta. So this is negative of the Wronskian. Okay, so this is nothing but minus v of zeta divided by p of zeta into w of zeta. where w of zeta is w of u of zeta into comma v of zeta. Okay, so simply we can write this as minus the vw divided by pw. Okay, also we obtain that here we already know that w equal to a by p of zeta. So for that uh, p into w can be written as over here we have p into w is equal to a, so we can replace it. So this is minus v divided by a, where v is a function of zeta, minus v of zeta divided by a, that is c1. Now to get C2, we can just replace the second row by the right hand side 0 comma 1 by p of zeta. So that will be here. The second row is replaced by this, and from this we get this is u of zeta divided by p of zeta minus 0 divided by negative of Wronskian. So this is minus u of zeta divided by p into w, that is minus u divided by pw, and we already know that pw is a, where a is a constant, so minus u of zeta c2, right, minus u of zeta divided by a, where a is p of zeta into w of zeta. Clear? Now the Green's function, thus the Green's function is given by, we already you obtained that Green's function is, we assumed that the Green's function g is c1 into u of x for x less than zeta and c2 into v of x for x greater than zeta. So here we have obtained c1 and zeta, c1 and c2, so we can replace that. Replacing that we have this is c1 and this is c2, so c1 is minus v by a and c2 is minus u by a. So replacing that here, you will get minus u of x divided by a into v of zeta minus u of x into v of zeta divided by a, where x is when x is less than zeta and when x is greater than zeta, when c2 is here, so minus u of zeta into v of x divided by a. So the Green's function g1 is minus u of x v of zeta divided by a. Here actually the Green's function is a function of x and zeta. Okay, so g1 is minus u of x v of zeta divided by a, and g2 is minus u of zeta v of x divided by a. Or you can write this g1 as minus u of x v of zeta divided by a. A is nothing but we have our a is p into w, so we can write this as p of zeta into w of zeta, Wronskian of zeta. This is g1, and g2 is minus u of zeta v of x divided by a, that a is p of zeta w of zeta, right? So we can either use this also, or you can use this only. This is the Green's function, where a is a constant independent of x and zeta, and which can be determined by this equation a equal to p into w. That is what is we obtained here, a equal to p into w, that is p of zeta into w of zeta. Okay, so this determination of this Green's function fails even only if this a is 0. If a vanishes, then this determination fails. So that that is the a equals 0 means the Wronskian is 0. This Wronskian is 0 means the u and v are linearly dependent. Okay, hence u and v are multiples of a certain non-trivial function of non-trivial function u, capital U. That is, if u and v are linearly dependent, then both u and v are multiples of a certain non-trivial function, capital U of x. In this case, the function u of x satisfies the equation L of y equals 0 and the boundary conditions. So we have derived the Green's function for the boundary value problem. So this is the Green's function for the boundary value problem. Ly plus phi of x equals 0 along with the boundary conditions. Here Green's function g equal to this g1 and g2 here, where a is p into w. Now our next aim is to find or to show that the function y of x is equal to integral a to b g of x zeta x zeta phi zeta d zeta is a solution of the boundary value problem Ly plus phi u of x equals 0 along with the boundary conditions of at x equal to a and p. That is, we have to show that this is actually the Green's function. So here we have to show that this y is the solution of the boundary value problem. Okay, B. So I think that we can discuss in the next lecture. Okay.